All right, we've arrived at section 14.8, the last section of the chapter and the last section of the book. We are now going to look at what's called the divergence theorem. We just finished Stokes' theorem, which was the three-dimensional version for Green's theorem in the circulation form. The divergence theorem is simply the three-dimensional version of the flux form for Green's theorem. So I'd like again to start by just reviewing the two-dimensional version. Here it is. If I have a two-dimensional vector field, R is a region in two space bounded by a closed curve C. So again, I've got some closed curve C. And I am really bad about saying this, but we have to travel counterclockwise. Then our flux, F dot n ds, is the double integral over the region R inside the curve of partial of f with respect to x plus partial of g with respect to y, dA. And this thing we gave the name the two-dimensional divergence. We hadn't yet studied divergence in general. We just looked at that as the two-dimensional example of it, and it still is. Again, let's think about what this was saying. Remember, the divergence measures how a vector field is spreading out. So if you have a vector field that's spreading out from inside R, then the flux is going to be positive. It's going to go outward across the curve. Of course, if the vector field was contracting, coming in, you'd have a negative divergence. But what's happening to that spread of the vector field, the divergence inside the curve, affects the flux across the curve. If you have a source in here, you're going to go ahead and it's going to be a positive flux. If you have a sink in here, it's going to be a negative flux. If your vector field is source-free, it doesn't produce, it doesn't expand, it doesn't contract, then you would have a flux of 0. We're going to three-dimensionalize that now with the divergence theorem. So now I have a three-dimensional vector field. D is a solid in 3 space, bounded by a surface, S. So let's say this whole thing in here is all my solid D. And the surface of the solid is S. We are now saying our flux, F dot n ds, across this entire closed surface, S, is going to be the triple integral over the solid D of the divergence of F dV. Notice this is essentially the same idea. If I happen to have a source inside my solid, my vector field is going to be expanding, and it's going to be pushing my material out across the boundary of the surface in all directions, and I'll have a positive outward flux. If I have a sink in here, I would have a negative net flux across that entire surface. Divergence is positive or expanding when I have a source. It's negative or contracting when I have a sink. So what's happening with the divergence determines what happens with the flux across the surface. Just a reminder, divergence is calculated as the gradient dot product with the vector field F. So our flux, our divergence theorem says calculate flux across a closed surface, and it must be closed, is simply the triple integral of the gradient dot product with the vector field. All right, so let's take a look at a couple of examples. And once again, I'm going to ask us to do this first one 2 different ways. We'll go ahead and find the flux for the vector field x squared, y squared, z squared across the surface of a hemispherical solid, bounded above by the sphere of radius 5 and below by the xy plane. Do the problem 2 ways, once by evaluating our surface integrals directly, and then a second time by using the divergence theorem. All right, so let's go ahead and first of all just visualize what's going on here. we've got this hemisphere of radius 5. The top is bounded above by that hemisphere and it's bounded below by the xy plane. So this is a closed solid. Both the hemispherical surface and then also this disk down here are boundaries. So if I'm going to go ahead and do this the old way, directly evaluating the surface integrals, keeping in mind I want the outward flux. I'm actually going to have to do two surface integrals here. I'm going to have to say S1 could be my disk down here in the xy plane. And then S2 could be the hemisphere itself. Didn't do that real well. I probably should have picked better colors. Let's see if I can make that look a little bit different than the hemisphere. There. All right. So let's go ahead and do the S1, the disk first. And then we'll do the hemisphere, and then we'll have to add the two pieces together. All right, S1 is this disk in the xy plane. So S is the surface, z equals 0, the xy plane itself. That means since this is already equal to 0, I don't need to work very hard to get the w this time. This is the w. And so my normal vector, the gradient of w, would be 0 with respect to x, 0 with respect to y, and actually I think I'm going to have to go with -1 with respect to z. I just realized I probably wrote that down wrong. Let me tell you just momentarily about why I chose that negative. We wanted the outward flux, and so I'm going to need my normal vector to point down, to be outward from that hemisphere. So I probably should have said instead of z equals 0, I could have gone with -z equals 0. It's the same thing, right? But that just gives me the downward normal instead. So we'll go 0, 0, -1 for our normal vector. All right, what about f? F was x squared, y squared, z squared, according to the problem. And again, this is going to be a double integral. So since the surface is z equals 0, z squared would be 0. All right, my flux is the double integral over the region R, which is going to be that disk, of f dot n dA and let's see, f was x squared, y squared, 0, n was 0, 0, -1. And in this particular case, it looks to me like we're just going to get 0. I'll get 0x squared plus 0y squared plus 0. So I'll get a 0 flux for S1. Let's try S2. That's the surface of the hemisphere itself. So let's see. In this case, we would have the surface is z equals, if I just solve my equation for z, I'd have the square root of 25 minus x squared minus y squared. And let's see, the outward normals this time are going to have positive z values. They're all pointing upward. So I should keep the positive z this time. To form the W. And then n is going to be the gradient of that W. And I'm going to have to write kind of small to fit all that in, but let's see if we can squeeze it in here. Let's see, the derivative with respect to x would be a negative 1/2. 25 minus x squared minus y squared to the negative 1/2 times negative 2x. Similar with respect to y. And then for z, we'd have a positive 1. So let's see, that negative 1/2 times negative 2x would be a positive x over that square root. Similarly for the y term. And the z term is just 1. So there's the n. And let me reset here. So I'm still working on S2. F, remember, was x squared, y squared, z squared. But again, I'm only allowed to use 2 variables in a double integral. So I'm going to plug in for the z squared. If I just solve the equation for my sphere for z squared, it's 25 minus x squared minus y squared. And so I had my n up here. And we've got our f here. So our flux integral is the double integral over r of f dot n dA. There's f. And n. And I'm going to go with the dA again one more time. All right. Let's see. I definitely do see some hints that maybe this is going to work out well with polar coordinates. Let's see. I think I want to go to polar. My r was that circle of radius 5, remember, in the xy plane. So let's try some polar coordinates. 0 to 5 and 0 to 2 pi. And this would be r squared cos squared theta. R squared sine squared theta. And that'll be 25 minus r squared. And then the dot product with r cos theta over the square root of 25 minus r squared, r sine theta over the square root of 25 minus r squared, and 1. r dr d theta. All right, we got it all set up. We're ready to start evaluating. So we've got our integral 0 to 2 pi and our integral 0 to 5. And I'm going to create my dot product now. Multiplying these first ones is going to give me r cubed cos cubed theta over the square root of 25 minus r squared. The second one would be an r cubed sine cubed theta over the square root of 25 minus r squared. And then finally I would have a plus 25 minus r squared. All right, unfortunately I did not get an integral that's very nice to do. I can't pull down the 2 pi for the thetas because I do have thetas in my integral. Instead of a sine squared plus cos squared, I have a sine cubed plus cos cubed, which is not nearly as nice. And this isn't an integral that's easy to do. If you want to play around with it, I'll tell you that it is doable by hand, but it takes a great deal of work. You actually have to factor this as a sum of cubes and go from there. It's kind of a big, ugly mess. But I'm going to say that since this is such a challenging integral, we're going to go ahead and rely on technology for this one. I don't believe that we've actually done double integrals on Maple yet, but I'm going to go ahead and say let's let Maple help us out with this one. So I'm going to go ahead and bring up my Maple screen. You know what, actually let's do one thing before we do Maple. Let's distribute this R through just so it's a little bit cleaner to type it in. So this is a common denominator. So I'm going to put those two terms together over that common denominator. And that's going to become r to the 4th cos cubed theta plus another r to the 4th sine cubed theta. And that'll become a plus 25r minus r cubed. There. All right, now if I go ahead, and that's what I'm going to type into Maple. I've actually already done it so that you don't have to watch me painfully type this all out, but you'll notice that I did use a double integral down here in the calculus menu, right here. I just went ahead and used that template, and then I just went ahead and put in my limits of integration. There's that 0 to 2 pi and that 0 to 5. Typed in my whole great big long integrand here, and I used a t instead of a theta. Just didn't want to have to go searching for the theta every time. And finally, I was able to get Maple to give me a result of 625 pi over 2. So here we go. And that's our flux across the, actually it's really our flux over the entire surface because we had 0 for S1, remember? So I'll just remind us plus 0 for S1. But that still gives us that as our final result. All right, so as you can see, not a very nice problem to do using direct evaluation. Let's try this now using this new divergence theorem. All right, I'm going to resketch because it's been a while. We had our hemisphere of radius 5, and it was a solid because it included both the disk in the xy plane as well as the hemisphere itself. So that's my D. And then S is going to be the surfaces of the hemisphere and the disk itself. If I'd like to go ahead and use my divergence theorem now to do this, I'm going to start by reminding us again that F was x squared, y squared, z squared. And I need the divergence of F to use the divergence theorem. That's our gradient vector dot product with F. So that's going to give me 2x plus 2y plus 2z. So there's my divergence. And the divergence theorem says that we can get the flux just by taking the triple integral over this solid D of the divergence of f dv. So let's see here. We would have, and I think we're going to go ahead and looking at this, I believe our best bet is probably to go with cylindrical coordinates. So let's think for a moment about this surface. This was x squared plus y squared plus z squared equals 25. So if I go with cylindrical coordinates, I'd have r squared plus z squared equals 25. And that means z is going to be the square root of 25 minus r squared. So when I go to set up my triple integral, I'm going to integrate this divergence function, and I'll change to cylindrical coordinates as I go. So this would be a 2r cos theta plus 2r sine theta plus 2z, z still is z in cylindrical coordinates, and then r dz dr d theta. Thinking about the solid, the z values go from the bottom, which is in the xy plane, or z equals 0, to the top, where z is the square root of 25 minus r squared. And then this circle of radius 5 down here is the r. So 0 to 5 for the radius, and 0 to 2 pi for the angle theta. So there's my setup. All right. I think probably the first thing I'm going to do is go ahead and, maybe I can do two things at once here. I'm going to try to integrate with respect to z, and I'm going to distribute this r at the same time. So I would get a 2r squared cos theta, integrating with respect to z is just going to put a times z on that, and a plus 2r squared sine theta. And again, when I integrate with respect to z, I'll get a multiplier of z on that, plus integrating with respect to z, that's going to give me a z squared times the r. So rz squared. And z goes from 0 to the square root of 25 minus r squared. And I still have the dr and the d theta. All right, let's reset with another sheet of paper here. All right, I'm going to go ahead and plug in the z value momentarily, but I'm going to notice that once I do, I'm going to have some really ugly r integrals. I'll have like r squared, and then I'll have a square root of 25 minus r squared, and so on. And those are not going to be integrals that are going to be easy to do. So I think it's actually going to be easier for me to do the theta integral by hand this time. Sine theta and cosine theta aren't hard to integrate. So since my limits of integration are constants, I'm going to go ahead and just swap them. I'm going to put the r integral on the outside and the theta integral on the inside. Okay, let's plug in that radical for the z's. So I'll have 2r squared cos theta times the square root of 25 minus r squared plus 2r squared sine theta times the square root of 25 minus r squared plus r, and then when I square that square root, that'll just become 25 minus r squared. Again, I swapped the order, so this is now d theta dr. Okay, I'm going to go ahead and do the theta integral. So let's see. I'll have here 2r squared, square root 25 minus r squared. And integrating cos theta is going to give me sine theta. Here again I'll have that 2r squared, square root 25 minus r squared. And integrating sine theta gives me a negative cos theta. Plus, all of this is constant with respect to theta. So I'm just going to distribute that and make that 25r minus r cubed all times theta. And theta goes from 0 to 2 pi. All right, let's see what we got here. Plugging in the 2 pi. The sine of 2 pi is 0, so that whole first term is going to become 0. Minus. The cosine of 2 pi is 1, so I'll get a 2r squared, square root 25 minus r squared times 1, plus 25r minus r cubed times 2 pi. Subtract, plugging in 0. Sine of 0 is 0, this whole first term is 0. Minus, cosine of 0 is 1. So I'll have 2r squared, square root 25 minus r squared times 1, plus, plugging in 0 for the theta here, 0 times anything is still 0. All right, getting close now. Let's see here. I have got, these two terms are identical, and it's this one minus that one, so that'll actually distribute and make that a plus. So those are going to add up to 0. And then the only other non-zero term I have is right here. So I'm going to pull the 2 pi out front, and then I've got 25r minus r cubed dr. That we can do on a calculator, although it's also not even hard to do by hand. And we ended up getting 2 pi times, hang on, let me plug that in my calculator. All right, that gave me 625 over 4. And of course, if I just cancel out a little bit there, that gives me 625 over 2 times pi, which is exactly the same result as we got when we used the traditional method, or the surface integral method. I'm again not going to claim that this was a ton easier. It was still a lot of work. Well, maybe it was a ton easier, because if you remember, last time we did this, we actually had to rely on Maple to do the integral, because the integral was so horrible we couldn't even do the first part by hand, much less the second. In this one, we were easily, well, not easily, but with a bit of work, we were able to get that first integral done by hand, and even this one wouldn't have been hard to do. So by using the divergence theorem, I took an integral that was absolutely awful to try to do by hand at all, and was able to turn it into one that I could have done the entire thing by hand if I had wanted to. There are other problems where the divergence theorem even does a better job for us of making the work a lot simpler, and our last example is going to show us one like that. All right, so here we go in example 2. We want the flux across the surface of the cube, defined by the absolute values of x, y, and z are all less than or equal to 1, for this vector field F. So let's see, x, y, and z all go between plus and minus 1. So I'm going to end up with kind of this cube here, going from plus to minus 1 on the y, plus to minus 1 on the x, and plus to minus 1 on the z. This is a really good example of a time when the divergence theorem is extremely valuable. This cube, of course, has 6 separate surfaces to it. So if I was going to use the surface integral method, I would actually have to do 6 separate surface integrals to finish this problem. But because it is a closed surface and encloses a solid, that solid cube, I'm able to use the divergence theorem and just do one integral, or at least a triple integral, but it's just one. So let's go ahead again, and just a reminder to ourselves, the flux here is the triple integral over this solid D, this cube, of the divergence of F dV. The divergence of F is the gradient operator dot product with F. Like so. And so the first terms, I'll get a derivative of 1. Plus the second ones, I'm going to get a plus 2y. And then the third ones, I'll get a plus 2. So I have 2y plus 3 for the divergence. So my flux integral, I integrate the divergence function, 2y plus 3. And again, all of my limits of integration just go from -1 to 1, since that's the dimensions of the cube in every direction, x, y, and z. And that's not going to be a bad integral no matter what order I choose to do it in. But I'm going to show you I can really do this kind of slick if I choose dz, dx, dy. I deliberately chose dy last because y is the only actual variable in the integrand. What that actually allows me to do is to use the shortcut on both of the first two integrals. So I'm going to keep this y integral, and then I'm going to say there are no z's anywhere in here except for the dz. So this one is just going to become the length of that interval. 1 minus -1 is 2. And there are also no x's anywhere in here. So this integral is also going to become the length of the interval. 1 minus -1 is 2. That's just like pulling down the 2 pi's. Same idea, right? I still have the 2y plus 3 and the dy left. So if I pull the 4 out, and then I integrate 2y plus 3, it's going to give me y squared plus 3y. From -1 to 1. And I could have done that integral on the calculator, but I haven't had to do that much work on this one, so I'll finish this one out by hand. Let's see, plugging in 1 would give me 1 plus 3. Plugging in -1 would give me 1 minus 3. What is that? 4 minus a -2, 6. Giving me a final flux of 24. So there's an example where the divergence theorem really helped us out a lot in terms of making this problem simpler. I did not have to do 6 separate surface integrals. Instead, I was simply able to do that divergence theorem. All right, that brings us to the end of section 14.8.